The topic of my talk is about the PerfektBlue attack that I discovered a year ago. This attack is a combination of multiple vulnerabilities that can be exploited to get remote code execution on millions of vehicles of different vendors. This includes Volkswagen, Mercedes-Benz, and many, many others. So let's begin with the introduction beforehand. My name is Mikhail. I'm a senior security researcher at PCA, mostly doing reverse engineering and vulnerability research. I have a keen interest in wireless technologies and kernels, and also I participated in multiple Pound-Town competitions and occasionally play CTFs. So, an infotainment unit, or IVI unit in short, provides various connectivity features to the end users, such as USB, WLAN, access point to client mode, Bluetooth, CarPlay, and Android Auto applications. Also, IVI is usually connected to other ECUs within the car through CAN bus. You can see an example of IVI unit on a slide. Now, let me describe the PerfektBlue attack in general terms. First of all, let's introduce the actual target, OpenSynergy BlueSDK product. This is a custom Bluetooth stack implementation, which is implemented in a modular framework manner. Hence, BlueSDK is adapted for each device separately, which might lead to differences between the implementations. From our analysis, it seems that BlueSDK is mostly used in automotive industry. This stack implements all the standard Bluetooth protocols, and the code is written pretty well, by the way. PerfektBlue is a universal, one-click remote code execution exploit that leverages 4 vulnerabilities found in BlueSDK. Exploitation of these issues bypasses all the standard security mitigations, such as ISLR, shadow stack, control flow integrity, well, depending on the implementation, and others. We confirm PerfektBlue presence on a number of IVI systems from Mercedes-Benz, Volkswagen, Skoda, BMW, and Audi. Our primary target for explaining the exploitation process will be Volkswagen ID.4, manufactured in 2022. This was the patient zero for the PerfektBlue attack, where I initially found the vulnerabilities. Here's some information about our primary target. The application responsible for Bluetooth communication is named BT-App. This is a 64-bit ARM ELF executable launched as non-privileged user. As you can see, all the default security mitigations are enabled, so it will be a good example of how PerfektBlue primitives can be used to bypass all of these mitigations. Now is the time to talk about the Bluetooth internals and its implementation in BlueSDK. Little disclaimer, all the code shown in this talk is pseudocode and not the actual source code. A lot of checks of the original code are omitted due to readability, and only mandatory exploitation steps will be discussed. In general, Bluetooth consists of several protocol layers. The lower layer is handled by a baseband controller, and the next layer is named L2CAP, which is basically the transfer protocol in terms of Bluetooth technology. These 2 layers are glued together using HCI layer, and all upper layers are based on L2CAP and implement various functionalities such as service discovery, audio-video transmission, and many others. Due to framework nature of BlueSDK, the pairing procedure is specific to each vendor. For example, BMW and Mercedes-Benz require opening a specific menu to allow incoming pairing requests, which is good from security perspective. However, in case of Volkswagen, Skoda, and Audi, an attacker can initiate the pairing procedure at any moment of time. This pops up a pairing menu, usually with 2 buttons, cancel and allow. If a user clicks cancel, an attacker can reinitiate this menu and do it constantly until the user clicks allow button. So this is kind of social engineering to force the user to allow incoming pairing requests. The protocol we'll be talking about is named AVRCP, which is based on AVCTP profile, and luckily for us, the latter one is out of scope for this talk. AVRCP defines how to control characteristics of a streaming media. This includes pausing, stopping, starting playback, volume control, and many other operations. It uses AVCTP as a transfer protocol for exchanging messages, and AVRCP utilizes commands and responses for communication. In our case, the control device in terms of AVRCP is IVI system, and the target is the attacker's device. This is a typical AVRCP frame format. There are many fields, but the most important ones for us are opcode, packet type, and parameter. Opcode defines an operation type for this frame. Packet type implies that there is a fragmentation logic in AVRCP layer, and parameter carries the actual transmission data. So the fragmentation map looks like this. Almost every protocol layer has its own fragmentation logic, which greatly complicates the communication over Bluetooth technology. The next important part of AVRCP is continue request. This command is sent by the controller after receiving a fragmented PDU from the target device. On each received frame, the controller asks the target for more data using this continue request. And this communication back and forth happens until the complete AVRCP PDU is reassembled. So we are done with the theoretical part, and now we'll be looking at the actual implementation of Blue SDK. Let's examine how AVRCP frames reception is implemented. This is the main function that parses response frames that were received by the target device. As you can see, there is a switch case for every packet type, and we will dissect them one by one. First, let's consider the case of a start frame, and I left only the code related to this functionality. The processing starts by allocating a control object named response PDU. Its structure is presented on the slide. A little note is that the malloc function adds a special header, so the final object size is usually larger than the allocation size. Then the function allocates a heap chunk for storing parameter data, as we've seen in AVRCP frame format. Then it goes into copy PDU fragment label after allocating all the necessary data. Within this label, it copies the parameter data into the allocated heap chunk. And basically, that's the end of the start frame processing. The next case is the continue frame. In the beginning, it reallocates response PDU parameter if it's necessary. And further, it copies the received data into the heap chunk. And finally, the end frame processing. Basically, its logic is identical to continue frame processing. And after all the data is received, the AVRCP PDU is considered as complete and can be processed further. In the reception function, invalid packet types go into the default case. In normal circumstances, it should drop such packets, but in this case, it still copies the received data into the parameter heap chunk. This is not a vulnerability, but a logic flow that we will use in our advantage later. Let's call it a pound frame type, a very original name, I know. Now let's examine the use after free vulnerability in AVRCP layer. First, we send a complete response PDU that will be parsed via parse response procedure. All the corresponding structures are presented on the slide. So the flow goes into parse response function, and if the specified response code that we control matches one of accepted, implemented stable, or interim, the free function will be executed. Within the free function, it must free the received response PDU. And first, it releases parameter object that is linked in response PDU structure. Then it frees the actual response PDU that is linked in the channel object. And as you can see, the channel has advanced response PDU pointer. However, after releasing the PDU data, it doesn't zero advanced response PDU pointer, and it still points to a freed memory of response PDU object. The next step is to send the pound frame, as we discussed previously. As we remember, in default case, it immediately copies the received data into the parameter. However, in this case, the copying will be made into the freed memory pointed by the parameter member. And additionally, the parameter itself is stored in the freed response PDU object. So the situation is like we take a freed object, take its freed member, and copy data there. This is obviously a use of the free condition that we have here. All right, so before going straight into the exploitation part, let's discuss heap spraying primitive that will help us a lot. In case of a start frame, it allocates two objects, a response PDU and the parameter. This is what we already know. As an attacker, we control the parameter length. And there is no validation that advanced response PDU is not 0 before the assignment. So the function just overwrites it without taking into account its previous value. Additionally, there is no upper bound limitation for parameter length, which means that we can spray the heap with controllable elastic objects using start frames. Each previous response PDU and its parameter are left in memory without references to them. And basically that's it about the heap spraying. The next task is to convert use after free condition that we have right now into a more powerful address write primitive. What we would like to have for address write is depicted on the right. We want to control a parameter pointer with an ability to write arbitrary data there. On the left, we have a references graph between the objects. The first step is to get UF condition by freeing response PDU and its parameter, as we already discussed. And further, we somehow substitute response PDU with the fake object that we fully control, which basically means that we control parameter pointer and can point it to an arbitrary memory location. And finally, we trigger the actual UF by sending the data of pound frame that will be written into the specified parameter pointer. Essentially, this high-level description explains what we would like to have for address write primitive. Of course, we have a list of problems with this approach. The first one is related to different libc versions among the affected devices. Some of them might use tcache for our object sizes, and others might use unsorted bin. And the solution to this is to make the exploit as universal as possible. Some of you might ask, if we have UF condition with object substitution, why do we need heap spraying in the first place? Well, there are several reasons for this. The first reason is consolidation of heap chunks. In case of unsorted bin, the free procedure will try to merge adjacent free chunks, creating one large free chunk. Of course, there are some exceptions to this rule, but generally that's the idea for heap defragmentation. Therefore, in case of malloc consolidation, UF condition that we have right now becomes quite unstable. I won't cover all the details, but believe me, a malloc consolidation can really mess up the exploitation process. On the other hand, we have tcache, which is used in modern libc versions. With tcache, there is no consolidation and heap chunks are not merged when they are free. The fact that tcache chunks are not merged greatly simplifies the exploitation process, and therefore, exploit needs to have a general approach to take into account both unsorted bin and tcache bin cases. The second problem is how these bins behave. Let's take a look at the unsorted bin first. Insertions that is free happen into the beginning, and deletions, that is malloc, happen from the end, which means that unsorted bin operates in a queue-like way. On the other hand, we have tcache that has several bins depending on the object sizes. All of these sub-bins are singly linked lists, which means that tcache bins behave in a stack-like way. For us, it means another layer of generalization we need to make in the exploit, because we want to have a universal exploitation approach that works both for queue-like and stack-like bins. So now that we have understood our problems, the solution to them is to empty specific bins before using them. And we can empty a bin by utilizing heap spraying primitive that we have obtained previously. But doing that, we don't need to differentiate between different libc versions, and the exploit steps will be the same for both cases. All right, so having a UF vulnerability, the obvious question is what object should we use for substitution? Let's consider UF victim and target objects. UF victim in our case is response PDU, where we want to control its parameter pointer. And UF target is the command parameter that will be used for substitution. I'd like to highlight that we will be using command parameter and not the command PDU itself. This is important. Both response and command PDUs belong to unsorted bin if tcache is disabled or not implemented. Now we will cover a step-by-step guide for the mentioned substitution. We imply that unsorted bin is used here, otherwise the steps will be the same with tcache as well. So after spraying, we have a list of objects, and unsorted bin is empty. Then we allocate a new response PDU, its parameter in fast bin range. After that, the command PDU is allocated, its parameter in fast bin range as well. Here we free the common PDU, and the object itself goes into unsorted bin, and its parameter goes into fast bin. Then we trigger UF condition by freeing response PDU and its parameter. The object itself goes into unsorted bin, and remember that free puts an object into the beginning of unsorted bin queue. After that, we allocate a new command PDU, but this time its parameter length is the same as response PDU, which basically means that we reallocate response PDU and we fully control its content because we control command parameter, which in turn means that we control parameter pointer and can point it to an arbitrary memory location. So that's the memory layout from the previous slide. And the final step is to send the pound frame to write arbitrary data into the specified arbitrary memory location. This means we have obtained arbitrary address write primitive. Additionally, we can trigger all these actions multiple times, so we are not limited to only one write here, which is really beneficial from the exploit development perspective. A brief summary of this section. Now we have heap spreading and address write primitives, and the latter one can be triggered multiple times. And all of this looks quite promising, right? Well, yes, but the problem is that PI and ASLR security mitigations are enabled, so we don't have any virtual address to write into. Obviously, we need to have some address leak to move on, and sometimes it's possible to do this having only one memory corruption vulnerability, but unfortunately that's not the case. Hence, we need to search for bugs somewhere else. And here comes another Bluetooth profile named RFCOM. RFCOM profile is used to emulate serial communications. It has a multiplexer channel used for managing connections and some control operations. For every established connection, there is a data channel which is used for exchanging data messages. In a multiplexer channel, there is a test command behaving similar to ping in TCP/IP. On the slide, you can see a typical communication over RFCOM protocol. There is a lot going on, but we are interested only in test commands, so don't study this slide very hard. Test commands are processed on sub-M and UA frame levels. Let's take a look at the implementation. Multiplex channel function is responsible for handling messages received on multiplexer channel. As I said before, we are interested only in test commands. So the function validates incoming parameter length, copy the received data into the global buffer, and then use this global buffer for sending test responses. The first vulnerability can be spotted pretty quick. If the incoming parameter length is too large, the function disconnects the channel. However, the function itself is not terminated after that, and the data processing continues regardless, which is a bug. The second vulnerability is the length used for outgoing data. The function uses sanitized copylen variable for copying data into the global buffer, which is good because the variable is sanitized. But when it sends data back to a remote peer, it uses unsanitized param_len variable, which can be larger than 0x7f bytes. So let me explain how these vulnerabilities work in a combination. In the beginning, we send a test command and get into multiplex channel function. The specified parameter length is larger than the received packet, so the size validation is not passed. In that case, it disconnects the channel using L2CAP disconnect, but the function is not terminated, and the processing continues. Then the copylen variable is calculated as the minimum value between param_len and 0x7f bytes. The received data is copied into the global buffer, and copylen is used as a length parameter for memcopy operation. Finally, the send test procedure is executed with unsanitized param_len specified as response length. This can exceed test response buffer, which is used for sending test responses. So does it mean we have out-of-bound reading with a possible address leak? Hopefully, yes. Let's examine this a little bit closer. So we have the following call stack in case of sending a malicious test command, and I covered L2CAP disconnect and send test functions. The vulnerabilities are presented on the slide. In case of L2CAP disconnect, the function processing continues without termination. And in case of send test, a wrong variable is used for sending test responses. However, we have unresolved problem with it. Internally, L2CAP disconnect function changes the state of the dynamic channel to disconnecting value, while send test function requires the channel to be in open state. The result of it is that nothing is transmitted to a remote peer, even both vulnerabilities are triggered. So let's examine this logic in a pseudocode. From L2CAP disconnect, we get into L2CAP disconnect request procedure. And after some sanity checks and validation, L2CAP disconnect request executes process disconnect request function. And exactly this function changes the state of the dynamic channel to disconnecting value. Later, in L2CAP send packet, the dynamic channel state is validated. As you can see, our channel doesn't satisfy the condition of open state. Therefore, nothing is transmitted to a remote peer, and triggering these vulnerabilities doesn't lead to out-of-bound reading. Well, on the slide you can see literally my face while looking at these vulnerabilities without getting any leak from the target device. Well, a brief summary of the RFCOM vulnerabilities. Both of them are logic issues, but due to finite state machine, we don't get any leak. And it's a dead end for us, and at that moment I was very desperate. But is it really true that we can't do anything? Fear not, we still have some chances in another Bluetooth profile, so let's not leave these vulnerabilities just yet. It's time to dissect L2CAP protocol, which is the transfer protocol in terms of Bluetooth. For each established HCI link connection, there is a corresponding L2CAP multiplexer channel, which is responsible for managing dynamic channel connections, disconnections, quality of service, and many other operations. Each dynamic channel is described by its channel ID, generated separately both for local device and the remote device. On the right, you can see an example of establishing a dynamic channel to service discovery profile. In the beginning, a new HCI link connection is created, followed by L2CAP channel establishment. As you can see, both device A and B has separate channel IDs generated for this specific dynamic channel. After that, devices configure the channel with MTU values, channel types, and all other information. And finally, the actual communication happens over the established channel. So let's examine how channel IDs are assigned in L2CAP protocol of BlueSDK framework. The function responsible for handling L2CAP state machine is presented on the slide. Each dynamic channel has its own state. This is what we already know. And the highlighted state is assigned after establishing a new channel. At this moment, the remote device received L2CAP configure response from the attacker's device. So the event name is self-explanatory. Finally, the function assigns remote channel ID of this specific dynamic channel based on the provided data. Notice that there is no validation on the received value for remote channel ID, which means that remote channel ID is fully controlled by us. Generally speaking, it's not a vulnerability on its own, but see what happens next. So imagine an attacker is connecting to the target device, HCI link connection was successfully established, and optional pairing procedure completed. In that case, the target device sends L2CAP connection request to RFCOM profile of the attacker's device. And this connection logic is pretty common after the pairing process is completed. And I've seen this happening on the major number of devices. Channel ID on a target device is OX40. Then the attacker responds with L2CAP connection response with its channel ID specified as 0. So the L2CAP channel will be described by OX40 and 0 pair. Then the devices configure the channel, nothing really interesting here. And finally, the L2CAP RFCOM channel is considered as fully established. A remote channel ID for the target device is assigned as 0, and basically that's the impact of this vulnerability. A brief summary of the L2CAP vulnerability. Attacker controls what channel ID is assigned as remote channel ID for the target device, and Bluetooth specification says that null identifier shall never be used, but we found a way how to use it. The bug itself looks completely harmless, and what possibly could go wrong? So now it's time to chain all the logic bugs we've gathered so far. Hopefully you remember what we had in rfcom test comment logic. There are two vulnerabilities for out-of-bound reading, but L2CAP state machine prevents us from doing so. Taking into account channel ID vulnerability, how does it affect the L2CAP state machine logic? Coming back to these three functions we've covered in rfcom part, two of them process disconnection functionality, and the last one sends test responses. So we get into L2CAP disconnect request from multiplex channel after receiving a malicious test comment. This is a long sentence, I know. And now the L2CAP channel ID vulnerability comes into play. The highlighted validation is passed by setting remote channel ID to 0, as we did previously. In that case, we bypass executing the function that changes the L2CAP channel state to disconnecting value, which means that channel state remains open. And finally, test response is about to be sent, L2CAP channel is valid, and the data is successfully transmitted to a remote peer. So here's the diagram to summarize the explained chaining. In the beginning, HCI link connection is established with the target device. Target device sends L2CAP connection request to rfcom profile of the attacker's device. We respond with 0 channel ID, triggering the first vulnerability in a chain. When L2CAP channel is established, we send a malicious test comment with large parameter length specified. We get into multiplex channel function, which handles multiplexing messages. Due to large parameter length, L2CAP disconnect function is executed, but L2CAP channel state remains unchanged thanks to the first vulnerability. Here comes the second vulnerability because multiplex channel function continues its execution after trying to disconnect the channel. And finally, the third vulnerability is triggered because parameter length is used for sending test responses instead of the sanitized copy length variable. And the result of it is address leaking after receiving test response from the target device. On the slide you can see the data we have received, but what are we looking at exactly? Some final information on rfcom protocol. Hopefully you remember test response global buffer, which is used for sending test responses. As long as we send data from this buffer and we have out-of-bound reading, we get data of client OpenQ member. And client OpenQ is a circular, doubly linked list, and if it's empty, it contains pointers to itself. Matching this with our leak, we can conclude that we have leaked the address of client OpenQ, which is located in rfcom max structure. In turn, rfcom max object is located within the BSS section, which basically means we have leaked the code address. Further, we can calculate the base address of our executable or library depending on how Blue SDK was integrated into the project. So in the mid-game, we have heap span and address write primitive plus virtual address of a code section. Our goal is to execute some code, and preferably the system function. And for this, we need to have system function address and a primitive for function execution. We'll begin with arbitrary function called primitive. Let's consider multiple candidates in the code and choose the best one. The first candidate is a callback execution in L2CAP notify profile procedure. Callback pointer of the manager object is buried very deeply in structures, so we need to locate it somehow, which is a problem in itself. Additionally, we can't really specify arbitrary first parameter to the callback execution, which is another problem. And finally, this procedure is executed very early in L2CAP frames reception, which might lead to application crashes. So it's better to skip this one. The second candidate is located in HCI link receive function. This one is executed even lower in Bluetooth stack, which can cause potential crashes or misbehaving. However, we can specify arbitrary first parameter this time, which is good, but still it's not good enough for us. Finally, the third candidate is shown on the slide. This one is executed in L2CAP connectionless event handler. This function traverses a list of special objects that contain context and callback members. Hence, we freely control what function is executed, and we also control its first parameter. Additionally, we also regulate time of its execution, which is really nice. Which means that this candidate is great for our arbitrary function call primitive. Last note is that the address of connectionless handlers list can be calculated from our code address leak. And the last primitive we need for comfortable exploitation is address read. Let's describe how to obtain it. The target procedure will be examined is named avtp send response packet. The logic behind this function is to send avctp responses to a remote peer based on the provided channel object. My idea for address read primitive is to utilize arbitrary function call to execute such a function that accepts only one parameter. This parameter is used for outgoing data. No writes happen into the specified read address. And finally, it sends specified data to a remote peer. With this environment, we will get clean arbitrary address read. So as you can see, the target function accepts AVTP channel that internally incorporates AVTP packet, while BT packet member will be used for sending outgoing data. All of them can be placed in memory using address write. In the beginning, function obtains a pointer to AVTP packet that we control. Then, based on TX data member of AVTP packet, the data pointer of BT packet is initialized. After that, the data length of BT packet is assigned based on packet size specified within the AVTP channel. Finally, the initialized BT packet is transmitted to a remote peer. As long as we control data pointer and its length, we get arbitrary address read primitive. So we place two objects in process memory using arbitrary address write. And then we utilize function call to execute the target function. And by controlling the placed objects, we can read any process memory. This means we can obtain read-only segments and dump code of Blue SDK. Therefore, we don't even need to dump the chip firmware to reverse engineer the code. We can just leak it remotely and automatically tune the exploit offsets. So in the end game, we have obtained system function address and the ability to execute it with the controlled first parameter. Hence, let's just combine everything we have discussed and get remote code execution. In the end, the architecture of our exploit looks like this. First, we set up an access point, then we push a one-click Bluetooth exploit to get code execution, and fourth, we pass supplicant to connect to our access point. And finally, we launch a reverse shell on top of it. So this is a pre-recorded video of me exploiting Volkswagen ID4. In the beginning, I demonstrate how to pop up the parent menu and do it constantly. So when AVI system shows a parent menu and I click cancel button, like this, the exploit will reinitiate this parent menu until I click allow button, like this. Then the exploit leaks the code address utilizing vulnerabilities in L2CAP and RFCOM. And after that, it sprays the heap and shapes some control objects to obtain the described primitives, address read, write, and function call. And finally, we will upload some files over TCP/IP to get clean reverse shell. So the uploading takes some time. All right, so I got the reverse shell, and finally I will show an image on the IVI display. All right, so basically that's it. All right, so as you have seen, I was able to get reverse shell on Volkswagen ID4 with almost 100% exploit stability. I didn't mention this in the talk, but improving the exploit stability was really tough. All right, so the boring part is over, congrats, and now comes the funny part. We'll be discussing other targets and what needs to be adapted for the exploitation. Let's start with Skoda vehicles. We had a real car with the specified firmware version updated in 2022. PI mitigation is disabled for the IVI systems, at least at the moment of this research, so we don't even need half of the obtained primitives. That's the proof of the confirmed exploitation of Skoda cars. Keep in mind that other vehicles utilizing MIP3 IVI systems are likely to be affected. Moving on to Mercedes-Benz, In this case, all security mitigations are enabled, but that's not a problem for us with all the obtained primitives. The main problem was RFCOM max objects that have different structure, so the address leaking part needs to be reworked. We didn't have a real car, so the exploitation was made on a test bug. The exploitation proof is on the slide. The next target is BMW, and this case is interesting because we had multiple BMW cars, but we didn't have firmware for them. At the time of this verification, I was using a different address read primitive that was quite weak, which is why I couldn't leak the firmware at the time of this verification. So it was decided to test only address leaking part. Also, I didn't want to test memory corruption, not to crash IVI, because that might lead to malfunctioning, and I didn't want to do that. On the slide, you can see a successful address leaking part that was performed utilizing L2CAP and RFCOM vulnerabilities. Obtained code addresses are highlighted. And finally, Audi cars. We verified it like 1 month ago, so I couldn't spend a lot of time for the analysis before the talk. Bluetooth service is apparently under AppArmor rules, so direct execv syscall is blocked or seems to be blocked because of seccomp rules, I guess. RFCOM max objects also have different structure, but that's not a problem. So we know that we can't execute system function due to AppArmor rules. However, what we see right now on the slide is successful address read, write, and function call primitives all perfectly working together. Additionally, you can see that we can execute shell code within the Bluetooth process. And the first stage is a small shell code that uploads the second stage, and the latter one is a C compiled code, which means that we have limited remote code execution without direct reverse shell yet due to time limitations. And I like to note that it doesn't mean that the full exploitation of IVI is not possible. We just didn't have enough time to verify it. So what is possible impact of remote code execution on IVI? One-click remote code execution could lead to the face, obtaining phone book information, eavesdropping on external microphone, getting GPS coordinates, and listening to Bluetooth data such as voice calls. But anyway, the most important part here is the entry point to the car system. An attacker can perform lateral movement to other ECUs within the car, having code execution on IVI. And usually this can be done by exploiting additional vulnerabilities. So let's briefly describe possible implications of this attack. We start our attack by launching one-click Bluetooth exploit to get code execution within the Bluetooth process. Then we might get privilege escalation by exploiting more privileged services through IPC mechanism, for example. On the other hand, we can go straight into the kernel to get LP from there, of course, by exploiting some other vulnerabilities. And the third possible attack vector is the exploitation of a connected phone through CarPlay or Android Auto applications. Finally, an attacker could perform lateral movement to other ECUs within the car. It's highly dependent on the architecture of each specific car, so what I have described is the general approach. Fun facts about the PerfektBlue. The complete exploit became really large because of different constraints I needed to satisfy in the mentioned Bluetooth profiles. The discovery and the exploitation of these issues took me about half a year in total. OpenSynergy patched vulnerabilities in a few months, which is quite fast for automotive industry. And wait for the OSINT part in the next section. The shown affected vehicles is only the peak of an iceberg. So the conclusions. The list of the identified vulnerabilities is shown on the slide. All of them are publicly available with the corresponding descriptions. This is our disclosure timeline with the PerfektBlue. There is a lot happening, but eventually we notified OpenSynergy. They rolled out a patch in a few months. And then we went to notify each vendor separately while finding out more affected vehicles. And the resources section. On the left, it's PCA website with the overview of the complete PerfektBlue attack. And on the right is my website where I host the table with all potentially vulnerable devices that I was able to gather. I gathered this list in my free time, so you can go search your car there. And important note, I don't claim that all the vendors in the table are affected. It's a list of potentially vulnerable devices. Saying this just in case. And thank you guys very much for your attention and listening to me yapping from the stage. Don't hesitate to ask questions if you have any. And by the way, I guess you can make a photo of this slide so you have the links. Thank you.